Okay, great. So let's start then. Okay, so welcome everyone to TCS Plus. This is the last talk of the semester. And today's speaker is Jerry Lee. The organizers for TCS Plus are Thomas Vidic, Oded Regev, Clement Canon, and G. Kamat. And now we will go around the table and introduce all the groups. So first we have the group from Northwestern, sitting not too far from me. Hi, Northwestern, we can't see you. Okay, then we have the group from IIT Gandhinagar. Hello. Then we have Oded Regev from NYU. And then we have Shavaso also from NYU. So it's a group from NYU. Then we have Sena from University of Michigan. Then we have, oh, hello. Yes. And then we have the group from Caltech. We can't see you, but we assume you're there in thousands. Okay, we can see at least one person. Okay, and that's all. So, okay, so today's speaker is Jerry Lee, and Jerry is a graduate student at MIT, advised by Ankur Moitra. He has done some very good work on theoretical aspects of machine learning. And today he's going to tell us about how to learn high-dimensional distributions under presence of noise. So, Jerry?
All right, great. So yeah, thanks for the introduction. Very happy to be here. So today I'm going to be talking to you about robust estimators in high dimension without the computational intractability. This is joint work with Ilias, Gautam, Daniel, Ankur, and Alistair. So let's get started. So before I get started, let me just mention that if you have any questions along the way, please feel free to ask. All right, so without further ado, so here's the outline of the talk. I'm going to first introduce the problem, tell you what robust statistics are and what the gaps in knowledge seem to be, especially in high dimensions. Then I'm going to give you some fairly in-depth intuition, hopefully, about why it's even hard to detect anomalous data in high dimensions and how we get around these kinds of things. And finally, I'll sketch the details of the full algorithm based on the intuitions I give previously. Okay, so let's jump right into it. So before I talk about robust estimators in high dimensions, let me just talk about non-robust estimators in one dimension. So just regular classical estimators in one dimension. Let me start off with the following very toy example. Given n independent samples, x1 through xn, from some univariate Gaussian with mean mu and variance sigma squared, how do we recover this Gaussian? Okay, so to learn a Gaussian, all you have to do is you have to learn the mean and the covariance, or sorry, just the variance. This is in one dimension. So let's just take the empirical moments, okay? This is kind of the natural thing to try. And indeed, these things are optimal, right? It's a very well-known folklore fact. Now, given enough samples, these estimators converge provably to the truth with high probability. And in fact, the rate at which they converge is optimal. So they're known as Minimax estimators. Like as you take more and more samples, the rate at which the error decays cannot be improved beyond possibly constant factors. And these estimators are a very basic instantiation of a very general framework, very general classical paradigm from Fisher, from like the early 1900s or something like that. And they're maximum likelihood estimators. And what Fisher said was that these estimators converge asymptotically to the truth. These, fair enough. And in TCS and statistics, we still continue to discuss these kinds of things a lot. This is still a very powerful paradigm. We still consider a lot of different minimax optimal estimators, and especially in TCS, we consider a lot of things like how do we compute these things in polynomial time and other computational aspects of the problem. In this talk, I'm going to consider something somewhat orthogonal to these issues. First considered by Tukey, who asked, another natural question, which is, what if the model isn't the full picture of the world? What if the model itself is somewhat corrupted? Okay, what do I mean by this? There's a very general phenomenon in statistics known as model misspecification, which is the following, fairly basic observation that in the real world, things are often close to a Gaussian, due to things like central limit laws, but never truly Gaussian. Or more generally, suppose you're modeling some phenomena using some model that you made. Well, you'd like to think that the phenomena is almost the model, but you're probably forgetting some smaller order terms, so it's not quite the model, right? So here's kind of like the cartoon. I'm hopefully modeling some phenomena using this Gaussian, this bell curve, but more likely than not, I'm forgetting about some smaller order, subpopulation or something, and so there's some small bump somewhere. Actually, it's more likely that there's just kind of stuff all over the place that I haven't fully accounted for. And so really what we're getting is we're not getting samples from a Gaussian. We're getting samples from a Gaussian plus noise. Okay? And now the question is, okay, I have these estimators which work beautifully for Gaussians, but do they still work when I get samples from something which is not quite a Gaussian, something which is like in the neighborhood, perhaps, of a Gaussian? Okay? So to formalize this notion of Gaussian plus noise, I need some notion of what does it mean to be corrupted. And in this talk, we're going to define the following contamination model. So on the previous slide, I had this notion of like a Gaussian PDF plus noise. It turns out this is more or less equivalent to the following notion of corrupting the samples themselves. Okay, definition. We say a set of samples is epsilon corrupted set of samples of size n from a distribution f if they're generated via the following process. First, generate n independent samples from this distribution f, and then give them to an adversary, who then inspects these samples and changes an epsilon fraction of them in any way the adversary desires. Okay? And to tie this back to the intuition I was trying to paint previously, turns out that this is slightly stronger than, but more or less equivalent to the model in which we get samples from some distribution which is in a neighborhood of f. So formally, it's more or less equivalent to getting samples from some distribution with L1 or statistical distance about O of epsilon from your distribution f. I won't prove this, but this is not too difficult to prove. So this kind of hopefully ties it back into the picture I was giving previously. Also, this notion of noise is stronger than something known as Huber's contamination model, which is a very classical notion of noise. I won't define it, but it's good to know. Okay. So here's, and the goal of agnostic learning, or learning with errors, or sorry, robust learning, is given an epsilon corrupted set of samples, recover f as well as possible. Okay.
Just to make sure, Jerry, when you say it's stronger, you mean more general, right?
Yeah, it's I can simulate the the second adversary using the first adversary. Yeah. Okay. So here's kind of a picture of what's going on. So what I have here are I have samples, IID samples. These blue dots are IID samples from this Gaussian in one dimension, say, and these are just good old nice samples. All right, and now I give these samples to a very powerful but also very evil adversary. This is head coach Bill Belichick of the New England Patriots. If you're not football fanatics like me, you just need to know that this guy fits the character, Anyways, you give them to this guy, and what he does is he's allowed to change an epsilon fraction of them any way he wants. So Bill's going to look at these samples and say, no, I don't like these samples. I'm going to move some of the samples there. So you move some of the blue dots to the red dots. Okay? And now we get this set of samples without the colors. And now our goal is to recover the original bell curve as well as we can. Okay? Hopefully this makes sense so far. All right, so to complete the picture, we need one final thing. We will need a notion of distance, and throughout this talk, we will use L1 or total variation distance. Okay? This is also known as statistical distance, and it's defined to be the follows. So the TV distance between two distributions, f and g, is just up to a constant of a half, just the L1 distance between their PDFs. Okay, and for a number of reasons I won't go into, this is a very natural measure of distance for this problem and a number of other classical statistical problems. But if you're not too familiar with this notion of distance, don't worry too much about it, because we're going to consider very fundamental and very basic classes of distributions. And for these classes of distributions, learning the distribution and TV distance just roughly corresponds to learning the parameters with some appropriate scaling factors. Okay. And now I can formally state the problem. Problem agnostic learning is the following. We let script f be a structured class of distributions, say Gaussians or product distributions or whatever. And then we are given an epsilon corrupted set of samples from some unknown f in this class script f. And our goal is to output f hat, minimizing the TV distance between the true distribution and what we recover. Okay, so hopefully this model makes sense so far. If there's any questions, please. Okay, so let's move on. So now let me make this concrete. Let me go back to the toy problem I had before of learning a Gaussian, but now let me add this aspect of robustness. Okay, so now we let x1 through xn be an epsilon corrupted set of samples from a univariate Gaussian with mean, mu, and varying sigma squared. And again, we want to learn this Gaussian as well as possible. Okay, so can we do this? Well, let me even simplify the problem a bit more. Let me tell you what the variance is. Let me tell you that the variance is 1. Okay, so all you have to do is learn the mean. So can you do this? Well, what we were doing before was we just took the empirical mean. So one naive question one might ask is, does the empirical mean still work? And the answer to this is a fairly resounding no if you kind of think about it for a second. Just because Bill Belichick can move a point to positive infinity, right? Then the empirical mean is arbitrarily far away from what it ought to be. Okay, so the empirical mean is very non-robust. It is sensitive to even one corrupted point. But there's something simple that still works in this setting. It turns out if you think about it, the empirical median is nice and it works quite well. In fact, it works optimally. So here's the following folklore fact, which is not too hard to prove. Given an epsilon corrupted set of samples from a Gaussian with mean mu and variance 1, and suppose this set of samples is sufficiently large, then with high probability, this 0.9 will just mean high probability throughout this talk, the distance between the true mean mu and the median of the corrupted points is still at most O of epsilon. And it turns out this implies that the TV distance between the true Gaussian and the Gaussian that you recover is also O of epsilon. And this error is optimal up to constant factors. You can't beat this error. Okay? And similarly, if you want to recover sigma squared, or the variance, something called the interquartile range works for recovering it in the presence of this noise. Okay, so what I've just asserted to you is the fact that the median and the interquartile range are robust statistics for the mean and variance of a Gaussian, respectively. Okay, and the study of such statistics which operate even under this very strong adversarial noise is a very natural problem, and it's a very classical subfield of statistics dating back to the mid-1900s. Okay, and there's been a lot of work on this, and it's still a very active research area today. And for this talk, we're going to focus on 3 aspects of robust statistics. The first, and arguably the most important, is the recovery guarantee, which is the following question. Given an epsilon corrupted set of samples of sufficiently large size, what is the error I achieve, in recovery? And notably, unlike the traditional minimax rate kind of stuff, this rate will not go to 0 as we take more and more samples. Just because if I take more samples, the adversary always is allowed to corrupt an epsilon fraction of the points. So if I take more samples, the adversary also gets more power, because they get to corrupt a larger number of points. And it turns out, ideally, the error should be, as long as you measure it in TB distance, it should more or less be theta of epsilon, ideally. You can't really hope for better, and oftentimes you can get this. Okay? The second thing is runtime, right? As TCS people, this is something we care deeply about. Just how fast can I compute my robust estimator, I don't really care too much about its statistical properties if I can't compute it before the heat death of the universe. So this kind of stuff. And the final thing is sample complexity, which is how large does a set of samples need to be before I can get these recovery guarantees. In this talk, I'm not going to focus too much on this. I'm going to mostly focus on the first 2 things. But our algorithms do have nice sample complexity. I just don't want to get into it for simplicity. And to broadly overgeneralize the state of affairs, these issues and other things, such as breakdown phenomena, which I won't discuss, these things are generally well studied and well understood, at least for parametric families, in low dimensions. Okay, and I'm really talking like quite low, like 5 usually, and if we're pushing it, 10. Okay, but this begs a natural question, because nowadays many natural statistical and machine learning applications involve extremely high dimensional data. So for a concrete example, which is nowadays considered something like kind of on the smaller scale, microarrays have something like 10K genes. Okay, so now all of a sudden you're in 10,000 dimensions. And when I said 10 dimensions before, we really can't handle 10,000 with the current techniques. And in this setting, robust statistics are much less well understood. So for instance, consider the following natural generalization of the 1D problem I gave you before, but now in high dimensions. Now I want to learn a high dimensional Gaussian in the presence of noise. So formally, given an epsilon corrupted set of samples from some d-dimensional Gaussian with mean vector mu and covariance matrix sigma, the goal is to recover mu hat and sigma hat, minimizing the TV distance between the truth and what you recover. Okay? In fact, just as before, let me simplify the problem and tell you what the covariance is. I told you what the variance was before. Let me tell you what the covariance is now. Let me tell you the covariance is the identity. So these are nice spherical Gaussians. Okay? So it turns out that we just need to learn the mean, and we need to learn the mean in two norms. So we need to find a mu hat, minimizing the two norm between mu and mu hat. Okay, so what was known about this fairly basic problem? Well, recall that in one dimension, all we had to do was take the median. And as silly as it sounds, the basic problem here is that there's no good high dimensional notion of the median that gives us everything that we want. So for instance, there's something called the Tukey median, which is developed by the pioneering robust statistics back in the day. And this gets the right error guarantee, O of epsilon. This is great. Unfortunately, in general, the runtime of computing the Tukey median is bad. In general, in the worst case, computing it is NP hard. And we don't have any good algorithms. They all are very exponential into dimension. Okay, so this is bad. There's another generalization of the median called the geometric median. And the runtime of this is great. It's polytime. You can compute this in a polynomial time. In fact, as of this year, I believe you can compute it in nearly linear time. So that's great. Unfortunately, the error guarantee suffers. The error guarantee is epsilon square root d, right? And I want to stress that this root d factor is really killer, especially as d is large. So in a typical use case, people tend to consider, we like to think of epsilon as a kind of smallish constant fraction, say like 0.1 or 0.02 or something like this. And when d is like 10,000, all of a sudden this error guarantee is like greater than 1, right? And this is completely meaningless statistically, because any two distributions have TV distance at most 1 from each other, right? So this gives us no non-trivial statistical error guarantees in a lot of settings, especially as d grows. Right, so I want to stress that this is quite bad. And this is why people get stuck at dimension 10-ish, more or less. Okay, and more or less, it seems to me that all algorithms that people knew kind of fell into one of these two camps. Either their error guarantee was good, but the runtime was exponential in the dimension or worse, or the runtime was good, but the error guarantee lost this root d factor or worse. So for instance, the tournament, or some agnostic version of the tournament, gets error guarantee O of epsilon, but the runtime is again exponential in the dimension. Another algorithm called pruning, you can do in more or less linear time, but the error guarantee again loses its root d factor. And finally, there's a very popular algorithm in practice called ransack. And for the parameters that people run this for, you can run this in nearly linear time, but as far as I can tell, you actually don't get any non-trivial error guarantees in the worst case. This is not an important point, but anyways, the moral of the story is there's a lot of algorithms, but more or less all of them seem to either be computationally intractable.
Oh, hey, Jerry, can I ask a question?
Yeah.
So what is the dependence on like epsilon and dimension in these algorithms? Like, why can't they just take epsilon to be like sort of 1 over d, something like that, right? Like 1 over 100d or something like that. Is that
so
the runtime going to depend on epsilon, exponential, or something like that?
You mean in the runtime or in the error guarantee?
Yeah, so I cannot rescale the error guarantee to be like 1 over 100d or something like that.
Well, so epsilon is kind of an input to the problem, right? We're just given a data set with some epsilon fraction of the data set being arbitrary.
Oh, I'm sorry. Okay, good. Thanks.
Yeah. Okay.
one more question along the same lines. Can you say what pruning is?
So pruning is I'm actually going to describe this in more detail later, but it's just like remove all points which are obviously too far away to be from the Gaussian.
That's what I thought you're doing, but then why do you get epsilon? You should get epsilon squared, because this is error in the TV distance, right? Not in the parameter distance.
No, it turns out you will get epsilon root d. I'll go into this in a bit more detail in a second. Yeah. Okay. So yeah, so all known robust estimators for the mean and high dimensions were either computationally intractable, or they lost this dimension-dependent factor in the error, or worse. Okay. And so this begs the natural question: can you agnostically learn a Gaussian in high dimensions efficiently with no dimension dependence in the error? All right. And one of the main results of our paper is this is in fact possible. This trade-off is not necessary. Theorem: there's a polytime algorithm which, given an epsilon corrupted set of samples from a Gaussian. So I was talking only about unknown mean, but in fact we can handle both unknown mean and unknown covariance. So from a completely arbitrary Gaussian with mean mu and covariance matrix sigma. So given an epsilon corrupted set of samples from this of sufficiently large size, we can output mu hat and sigma hat such that with high probability, the TV distance between the truth and what we recover is this quantity. O of epsilon log to the 3/2 1 over epsilon. Okay? And I want to parse this for a second. Very importantly, there's no dependence on D in this whatsoever. So this is entirely dimension free. Also, it's quite nice. This error is like the best error you can hope for is O of epsilon. So we're only off by this log to the 3/2 factor. So actually quite good, at least in my opinion. Okay, let me make some further remarks about this result. So the paper is quite long, and this is because we also give a bunch of similar results for product distributions and mixtures of product distributions and mixtures of Gaussians and this kind of stuff. All the results are conceptually kind of similar. Everything gets a bit more complicated in these settings, and so I'm just going to focus on the Gaussian. I tend to find it's like conceptually the simplest class. I also want to mention, so we don't state it this way in the paper, but it's not too hard to see just from like going through it, that our results in general apply to robust parameter estimation under some moment bounds. What do I mean? Suppose I want to estimate the mean or covariance of an arbitrary distribution in the presence of epsilon corruption. Turns out we can do this assuming that you have, say, your distributions like sub-Gaussian, or maybe you can get some weaker results if you have, like, say, second or fourth moment bound and stuff like this. Okay. And finally, I want to mention that a concurrent work of Lai, Rao, and Paula, which also appeared in Fox this year, gives an algorithm for a similar problem cast in a more general setting, but they seem to get somewhat worse parameters. So I don't want to discuss too much about this, but we can compare. I'm happy to compare these offline if anybody's interested. Okay, so if there's any questions, if there's no questions, I'm going to start diving into the intuition of the technical stuff. Okay, seems good. All right, so for the rest of the talk, I'm going to try to understand how to learn the mean robustly. So I'm not going to focus on learning the covariance just because that's a bit trickier. So for the rest of the talk, let me focus on the following problem, which I gave you before. Given an epsilon corrupted set of samples from some d-dimensional Gaussian with mean mu and covariance identity, return mu hat minimizing the TV distance between mu and mu hat. Okay, and I said before that we want to learn mu in L2 norm, sorry. And this can be made formal using the following fact. So let epsilon greater than 0 be sufficiently small. Then the TV distance between two Gaussians with mean mu and mean mu hat and covariance matrix, both the identity. The TV distance between these two guys is at most epsilon, if and only if the 2 norm of mu minus mu hat is also less than O of epsilon. Okay, this is not too hard to prove. You can just kind of either do this explicitly or go through like some Pinsker's inequality kind of thing. So really, this problem is really just equivalent to learning the mean in 2 norm. Okay, so why is this so hard? Well, why do naive methods get stuck? Well, consider the following simple algorithm. This is a naive pruning that I think Oded was asking about. So this is just remove all points which are obviously too far away to be from the Gaussian and take the empirical mean of the remaining points. Okay, to make this an algorithm, to actually analyze it, we need to understand what this means. What does it mean to be obviously too far away to be from a Gaussian, right? So this is the only thing that we need to understand. So let's first do this in one dimension, okay? The following fact is pretty much straightforward from the definition of the Gaussian. So if x is drawn from a Gaussian with mean, mu, and variance 1, then the probability that x differs from its mean by more than square root log 1 over delta is less than O of delta. Okay? So what this means is that if you truncate all points at O of square root log 1 over epsilon, so just throw away all points which are, have distance more than O of square root log 1 over delta, square root log 1 over epsilon from the mean, then you have the following. The fact says you throw away only an O of epsilon fraction of the good points. And I don't know what's really happening with the remaining bad points, except that they survive the truncation. So they can be at most O of square root log 1 over epsilon away from the mean as well. And there's only an epsilon fraction of them, which means that they can only contribute an epsilon times square root log 1 over epsilon error. Right? So this kind of sketchy argument hopefully justifies the fact that the empirical mean of the truncated points satisfies that the distance mu hat minus mu is less than O of epsilon square root log 1 over epsilon. Just because I haven't thrown away very many good points, so the good points still concentrate quite nicely to mu, and the bad points, again, I don't know what they're doing, but there's only an epsilon fraction of them, and each one is at most O of square root log 1 over epsilon away from the mean. Okay, so what goes wrong in D dimensions? The problem is that this fact loses these root D factors just kind of inherently, right? In D dimensions, the fact changes. If x is now drawn from a Gaussian with mean, mu, and variance identity, then the probability that x minus mu in 2 norm is greater than square root D log 1 over epsilon is less than O of delta now. Sorry, square root D log 1 over delta is less than O of delta now. So, and this root D here is really inherent, right? Most points from a Gaussian will be about root D away from the mean in D dimensions. What this means is that you need to truncate at square root D, right? Log 1 over epsilon. And when you do this, you still only don't throw away that many good points. Now the bad points are super far away from the mean. They're all square root D log 1 over epsilon away from the mean. And that means the empirical mean of the truncated points is quite large, right? The distance is now you lose this root D factor. And this is more or less inherent in the approach.
But endpoints is going to be like basically all concentrated within distance of roughly root D, so they cannot be too close as well, right?
Yes, exactly. And so this root D is like really there. And so when you truncate at this, like the bad points are really going to be in this root D. So give me a second, I'll show you a picture, which is just saying what you're saying.
Mm-hmm.
So in low dimensions, we like to think of things as being a nice bell curve. And so most of the good points are really close to the mean. And so in particular, if the bad points want to pretend to be good points, they also have to be pretty close to the mean, right? And so because they have to be pretty close to the mean and there's not too many of them, then they can't really do too much to screw us up. But in D dimensions, I can't really draw it here. What's going on is that everything is concentrated in this kind of shell of radius root D around the mean. Even the good points are all pretty much in this shell. And what this means is that the bad points should also, if they want to pretend to be good points, live in this shell of radius root D around the mean, right? And so that means now you have an epsilon fraction of points. Each one is about root D, and they're all bad, and we don't really know what they're going, So that's how you lose an epsilon root D factor. And this seems really hard, right? Like if I erase these colors and I ask you to identify which points were good and bad, you really can't do it because each one of these red points just individually looks potentially like just a good old point from a Gaussian, right? So hopefully what I've argued for you, at least at some intuitive level, is that any method that only looks for outliers on an individual basis must get stuck at this barrier of O of epsilon root D, just because of that picture I showed you. And so to progress beyond this, you need to look for corruptions on a more global scale, right? The kind of sketchy intuition is that an outlier is not only an outlier just because of how far it is potentially, but also because of its interactions with other points. If there's too many points in this one direction, then they collectively suggest some outlier behavior, right? And this kind of interaction suggests using a higher moment method, and this is what we do. So our idea is the following. If the corrupted points move the empirical mean by more than O tilde of epsilon, then we show that they must also screw up the empirical covariance in some very noticeable way. Okay, and this is kind of the crux of the idea, at least for unknown mean. So here's the proposition that makes this a bit rigorous. Given an epsilon corrupted set of samples from a Gaussian with mean, mu, and variance, a covariance matrix identity of size n, where n is this number, don't worry about it, but this is what you need, and yeah, it's pretty much optimal. Then let me form the empirical mean and empirical covariance of these corrupted set of points. Okay? The proposition says the following. With high probability, if the two norm between the true mean and the mu hat, the empirical mean, is large, is at least omega of the epsilon square root log 1 over epsilon, then the spectral norm between sigma hat, the empirical covariance, and what it ought to be, which is the identity, because that's what it ought to be, the spectral norm of this difference should be also large. It should be at least omega of the two norm between mu and mu hat squared over epsilon. And if you plug in what this is, then you get that this two norm is at least, this spectral norm is at least omega of epsilon log 1 over epsilon. Okay? So what this is saying is that, if there's no corruption, this would never happen. This spectral norm would never be this large. Okay? So this spectral norm gives kind of like a red flag saying that, oh crap, the bad points are doing something bad to the mean. Okay? This is kind of how to parse the proposition, at least. This is my interpretation of how to parse it. I want to mention one kind of subtle thing. When I say with probability 1 minus delta, I will always mean just with probability 1 minus delta over the original uncorrupted points before the adversary touched them. Okay, so I want to make no assumptions about which points remain or anything like that. I don't want to make any assumptions about what the adversary did at all. Okay. Hopefully that makes sense. All right, let's start proving this. Before I do that, let me make one notational simplification. Let me assume the true mean is 0. Okay. So all I've done here is I just made mu 0 everywhere. So now the proposition states if the empirical mean has large 2 norm, then the spectral norm of sigma hat minus identity is also large. It's at least the 2 norm of mu hat squared over epsilon. Okay. So throughout the proof, mu will be 0. All right. So let's jump in. Let me define the following notation, first of all. Let me let S bad be the indices of the corrupted points, and let me let S good be the remaining set of indices. Okay? So by definition, there's only an epsilon fraction of bad points. So that means the size of S bad is epsilon times n. Okay? Now we have the following two concentration inequalities about the good points. So the first lemma says that with high probability, the empirical mean of the good points is small. Recall it should be 0. Okay, so the empirical mean of the good points is at most O of epsilon square root log 1 over epsilon and 2 norm. The second lemma says that the empirical second moment of the good points, recall it should be the identity, the deviation from the identity of in spectral norm of this empirical second moment of the good points is also small. It's less than O of epsilon square root log 1 over epsilon as well. Okay. I want to pause here to make there's a kind of subtle thing going on here. In that, so the good points are the points which are uncorrupted. But just because they're uncorrupted does not mean that they are uncorrelated anymore. And this is because of the kind of subtle thing. Because if, the adversary chose which points to corrupt, so they also got to choose which points not to corrupt. And this kind of causes some potentially non-trivial correlation between the good points. So this is why we get these square root log 1 over epsilon factors, because we need to union bound over all possible choices of which things the bad points, were removed. Hopefully that made sense. If that didn't, then that's okay as well.
Hey, Jerry, sorry, I kind of missed the adversarial definition, but is there any substantial difference between corrupting the distribution in advance versus corrupting it after you see the samples, which I assume what your definition is?
Oh, yeah. It's like slightly stronger if you allow the adversary to corrupt the samples afterwards, but not in any meaningful sense that we know of, I think, as far as we can tell.
Oh, I
so
see.
More or less you can think of it as being, corrupting the distribution.
All right, cool, thanks.
Yeah. Okay, so yeah, but, this kind of subtle thing is why we lose these square root log 1 over epsilon factors. We need to kind of union bound over all possible choices of the bad points.
Jerry,
Oh, sorry. Yeah.
so could you get rid of your square root log 1 over epsilon if you move to the model where the points were corrupted before they were seen, where they corrupt the model instead of the outcomes?
So okay, so there's kind of subtle things going on here. If you actually allow arbitrary corruptions of the model, it's still not true that you can remove this, I believe, because you can like have like added like corrupting the distribution in L1 corresponds to like adding some things and removing some things. There's a weaker model. This is Huber's contamination model, where it's just like a mixture of the good points with some small bad population, and in that setting, you can remove these.
Okay,
thanks for this. Yeah. Okay. So for the rest of the proof, let us condition on the fact that the previous two inequalities both hold.
Here,
Yeah.
just one more question. Is there really no dependence whatsoever on dimension?
Yeah. This is what makes like the proofs a bit messy, but yeah, there's no dimension dependence here. Because you're union bounding, if you do the union bounding properly, it just kind of falls out. Yeah.
But just to make sure again, the variance is identity, right? So those vectors are typically of length square root d.
Yes. Well, no, this one, this one, it will not by this lemma. And this thing, we're still considering a spectral norm. And in spectral norm, it turns out everything's kind of okay.
Yeah, I'm still with the first lemma. So the xi's individually would be of length square root d.
Yes, but it turns out in aggregate, they won't.
I'm just confused because assuming there are enough dimensions.
Yeah.
You always have a dimension where, say,
so like
it's a positive, right?
Right. So more or less, what's going on is, certainly if we take enough samples, then this will happen for the good points if there are no corruptions, right? And what the concentration lemma shows is that if you remove a small fraction of these good points, the remainders still concentrate really well because Gaussians have really nice tails. This is more or less what's going on. Yeah, we can perhaps discuss it more offline.
Okay, thanks.
Yeah. All right, so for the rest of the proof, we will condition on the following two inequalities both holding, and we can do this just by union bounding over their failure probabilities. Okay, so now I will prove the following lemma. If mu hat, the two norm of mu hat is large, it's at least omega of epsilon square root log 1 over epsilon, then we have the following, which is that the empirical second moment of the bad points has large spectral norm. Okay, it's at least 2 norm of mu hat squared over epsilon squared. All right, and this is the key lemma for us. Let's see how to prove it. Well, just by assumption, we have the 2 norm of mu hat. And what is mu hat? Is this average of all the points. So let me just split this up into the good points and the bad points. By assumption, this has large 2 norm. It's at least this. Okay, but the good points, we know they concentrate. This term has small spectral norm. It's at most O of epsilon squared root log 1 over epsilon. So, if this is a constant factor smaller than this, just by choosing the constant factors properly, that means the second term must contribute at least a constant fraction of the 2 norm of mu hat. Okay, so this implies that the second term here, which is just 1 over n times the sum over the bad points of xi, has large 2 norm. It's at least omega of the 2 norm of mu hat. All right, now let me do the following. Let me just multiply and divide both sides by the sides of it, or this by sides of s bat. Recall s bat over n is epsilon because s bat is size epsilon times n. So I can move this over, and I get the following. Right there, the empirical mean of the bad points has 2 norm at least, 2 norm of mu hat over epsilon. Okay, but I want to bound the spectral norm of the empirical second moment. So how do I relate this quantity to the empirical second moment? We use the following elementary fact, which is that if v1 through vm are arbitrary vectors, then the empirical second moment of these vectors, so 1 over m times sum vi va transpose, is psd greater than or equal to the empirical mean of their vi's outer product itself. Where psd greater than or equal to just means that this difference is a psd matrix. Right, so hopefully this is understandable. It might look a bit complicated, but it's really just a natural generalization of the univariate fact that the expectation of x squared is greater than the expectation of x quantity squared. Okay, and you prove it the same way. All right, so if you believe this lemma, then let's just plug in the bad points. Okay, and what this says is that this empirical second moment of the bad points is PSD greater than or equal to the empirical mean of the bad points at a product itself. Right? One thing that this PSD greater than or equal to implies is that the spectral norm of this is at least the spectral norm of this. This implies this. And the spectral norm of this, well, this is just a rank 1 matrix, right? It's just some vector out of product itself. So the rank 1, so the spectral norm of this is just the 2 norm of this vector squared. So it's just this. And the 2 norm of this vector is the thing that we just lower bounded. So we just plug in that bound, and we get this following bound. Right? So this proves that the empirical second moment of the bad points has large spectral norm. Hopefully that made sense to people. But now let's see how to use this lemma to prove the full proposition. So recall what we wanted to prove was that if the 2 norm of mu hat is large, then sigma hat minus identity has large spectral norm as well. Well, how do we prove this? Well, let's just write things out. So sigma hat minus identity is this thing, just by definition. By some elementary manipulations, you can show that this is actually equal to the empirical second moment of the xi minus mu hat transpose minus I. This is just by like multiplying out and canceling things, okay? And then, sorry, things are gonna start moving because my LaTeX foo is not great, but what I just did here is I split up xi transpose into the good points and the bad points. Okay, so nothing, I still haven't done anything fancy yet. Then I'm going to multiply and divide this by size of S good and multiply and divide this by the size of S bad and use what I know about how large they are to get these things because, size of S bad is epsilon times n and size of S good is 1 minus epsilon times n. So I get this. So again, I still haven't done anything fancy. I'm still just doing elementary manipulations. And I'm going to do one final thing. I'm going to move this identity into this term. So there's a 1 minus epsilon out front, so I'm going to have a remainder of an epsilon times identity. Okay, so I still haven't done anything fancy here. This is just like, I can just derive this expression just by moving things around here. Okay, now I claim that the third term is going to dominate everything spectrally. So the third term is the thing I lower bounded previously. The third thing without this epsilon in front had a spectral norm at least a 2 norm of mu hat squared over epsilon squared. So when I multiply by epsilon, it has spectral norm at least this 2 norm of mu hat squared over epsilon. And by assumption, this is at least omega of epsilon log 1 over epsilon. Okay, I claim this term is spectrally bigger than everything else. Well, how do we see this? Let's just do it term by term. The first term has small spectral norm just from our concentration inequality, right? This has spectral norm at least at most, epsilon square root log 1 over epsilon. So this is clearly smaller than this. Good. The second term is epsilon times the identity. The spectral norm of this is epsilon. So clearly this is smaller than epsilon log over epsilon. And finally, the spectral norm of mu hat transpose, again, this is a rank 1 matrix. So the spectral norm of any rank 1 matrix is just, mu hat 2 norm squared. And this is clearly smaller than mu hat 2 norm squared over epsilon. So again, this term is dominated by this term. So all 3 terms individually are smaller than this. So by losing some constant factor, this term dominates their sum as well. Right? Hopefully that makes sense. And this shows that the operator norm of sigma hat minus identity is at least omega of 2 norm of mu hat squared over epsilon, as we claimed previously. Okay. Any questions? Did that make sense to people, hopefully? Okay, moving on, I guess. What I just showed is that we can detect whether or not the empirical mean is off from what it ought to be just by checking the spectrum of the empirical covariance. Or another way to phrase it, if the empirical covariance is really close to identity and spectral norm, this gives a certificate that the mean must be close, the empirical mean must be close to the true mean, right? So this gives us like a nice stopping criteria, but it doesn't actually give us anything algorithmic yet. Right? It's not clear immediately, at least to me, how to use this algorithmically. And indeed, this requires a couple of new ideas that I'm going to discuss now. Okay. So we give 2 algorithms motivated by this intuition. The first is a filtering or sort of like iterated rejection sampling kind of approach. And this runs in O tilde of nd squared time, so it's actually quite fast. But our current analysis of it is says it's not sample optimal. It requires more than the sample, optimal number of samples. The second algorithm seems to be a bit more careful with samples, but it's slow. I mean, it runs in polynomial time, but this is like, a theorist polynomial time. So well, you wouldn't expect it to run in practice. But it's sample optimal up to like log factors. And the shared intuition between these two approaches is the following. We're just gonna check the spectral norm of sigma hat minus identity. Right? If it's small, then the original proposition says that the empirical mean is close. But if it's large, well, how can that happen? Let's just look at the top eigenvector of sigma hat. If it's large, if this spectral norm is large, then in that direction, the data points must have like a lot of variance, right? But how can that happen, right? The good points when we project in this direction are still Gaussian. So they're still nice. They still concentrate nicely. They don't have too large variance. So the only way the variance in this direction can be large is if the bad points are like really far out on average. And that means that this direction is the direction in which the bad points kind of dominate. And this gives us some like non-trivial information that we can use algorithmically. Okay, let me make this rigorous in a second. In fact, the filtering approach kind of just explicitly does this. So we execute the following while loop. While the spectral norm of sigma hat minus identity is large, so at least omega of epsilon log 1 for epsilon. Then we find the top eigenvector of sigma hat, or some approximate top eigenvector of sigma hat. And we do the following. We project all the points in this direction. And then you can show that there's some threshold t such that the number of bad points, which are larger than t in this direction, the number of such bad points is strictly larger than the number of good points, which are large in this direction, which are bigger than t in this direction. Okay, and this t is just some violated tail bound. It's going to be some like violated Chernoff bound kind of thing. And then what do you do? Well, we found this t, and then just throw out all points with xi.v greater than t in absolute value. And by this guarantee, this implies that we throw out strictly more bad points to good points in every iteration. And this does everything that we want.
Jerry, so do you show that there exists some t, or that you can find it just given the samples?
We can find it, yeah.
Okay.
Yeah, there's some inequalities you need to check here that I haven't written out, but it's really just some violated tail bound. Okay, so because we throw out strictly more bad points than good points, this loop cannot go on forever and cannot throw out too many good points. And so when the loop terminates, let me just return mu hat, which is the empirical mean of the remaining points. And because we've exited this loop, this means that the spectral norm of sigma hat minus identity is small. So by our proposition, the empirical mean is close to the truth. Okay. So the really nice thing about this algorithm is that it's fast. It runs in O tilde of nd squared time, and this is potentially practical. So recall, so n is the number of samples, and each sample is a d-length vector of numbers. So just to read the entire set of samples already takes nd time. And so what we're doing is we're just reading the samples d times. Okay. And this is not obvious from the description I gave previously, but you can show that the while loop will only execute for O of d iterations. Okay. And moreover, you can do each iteration in nearly linear time using these approximate PCA techniques. Unfortunately, the algorithm is a bit aggressive in throwing away samples. The analysis in the paper says it requires O tilde of d cubed over epsilon squared samples. Ilias tells me that you can improve this to d squared over epsilon squared samples using some VC theory techniques. I would need to check this, but regardless, that's still not sample optimal. More or less, this is because at least our current analysis requires concentration of these linear threshold functions in Gaussian space, which requires a lot of samples. But I conjecture, at least, that either the analysis can be improved or there's some simple modification of this algorithm, probably, that gets the right sample complexity. That would be very nice. I would like that a lot. Okay. The second algorithm is a bit more complicated to describe, but it's based on convex programming, and it's a kind of a smoother version of the filtering, which is just, the idea is to give weights to each sample point and adjust the weights if we think they're contributing to the noise. So down weight the weights if they're contributing to the noise, and make them bigger if we think they're good. Okay, so to describe the algorithm, I need a bit of notation. So for any set I in 1 through n, let me let W sup I be the set of weights which are uniform over I and 0 otherwise. Okay. And now, okay, so ideally I want to put the uniform weights over the good points, right? And I know that there's 1 minus epsilon times n good points. So let me just take the convex hull over all the uniform weights over 1 minus epsilon times n points. And now I'm going to consider the following convex set. I'm going to take the set of weights such that if I take the empirical covariance of these weights, except I plug in the true mean here, and I subtract out the identity, the spectral norm of this quantity is at most delta, where delta is some parameter. So you can show, it's not too hard to show that if you can find a W in this set C sub delta, then by kind of the same techniques as the proposition, you can find something which is close to the true mean. Unfortunately, this is an unknown convex set because we don't know the true mean mu. Right? That's the whole point. However, you can show that using these kind of spectral techniques, you can give an approximate separation oracle for this set. And this suffices to find a point in the set, or approximately find a point in the set, using like ellipsoid or cutting plane methods. Okay, so I went over that a bit quickly, but yeah, that's more or less I'm going to talk about for the convex programming. The nice thing about this algorithm is that it's quite careful with the samples. It never like throws away things or anything like that. So it seems to only require O tilde of D over epsilon squared samples. And up to log factors is the sample optimal for the problem. Okay. And unfortunately, because we use these ellipsoid and cutting plane methods, it is poly time, but the algorithm is quite slow.
Jay, what is the convex? What is the program convex in what variables? Because mu is unknown.
It's convex over the WI, the weights. We're going to optimize over the WI.
But the mu is unknown.
Right. So we're just, but for like a ellipsoid or cutting plane method, all you need to do is you need to find a separating hyperplane, right? So if you can produce this, even if you don't know C sub delta, you can find a feasible point in the set.
Mu is the empirical, mu is the mean obtained by the W's.
No, mu is the true mean. So we don't know C sub delta. Our goal is to find a point in C sub delta, but C sub delta is unknown to us.
Sure. Okay.
So we're going to just use traditional techniques, like these ellipsoid algorithms allow us to find feasible points in convex bodies without knowing the description. Right? If I can like produce a separating hyperplane at each step for my like current guess, then I can approximately find a point in C sub delta. This is
and how is the separation oracle defined? So
it more or less it's pretty much just take the top eigenvector of this.
Okay. Okay.
Or sorry, take the top eigenvector of this, but with mu hat instead of mu.
Okay.
Yeah.
That makes sense. Okay. Thanks.
Yeah. Okay. All right. So now let me briefly touch about unknown covariance. At a high level, we're doing kind of the same kind of ideas. So let me let mu be 0. So all we need to do is recover the second moment. So previously, the idea was for the unknown mean, if the corrupted points move the empirical mean by more than O tilde of epsilon, then they must also screw up the covariance, right? And it turns out more or less that you can still do this just one level up. So now you can show that the empirical points, if the corrupted points move the empirical covariance by more than O tilde of epsilon, then they must also screw up the covariance of the covariance, which is some sort of flattened fourth moment tensor of the Gaussian. And similar ideas are involved, but the techniques are more complicated just because these objects are uglier, and this causes a bunch of pain for students, postdocs. Okay. We also do something for product distribution. So a product distribution over the hypercube is just a distribution where every coordinate is independent. Right? So this is also determined uniquely by its mean. So you might think we just need to learn the mean. And indeed, similar techniques to the unknown Gaussian case allow us to learn the mean to error O tilde of epsilon and L2 norm. And this almost suffices. So in the Gaussian case, it sufficed. But in this case, it does not entirely. Because if like coordinates of the mean are really close to 0, 1, things break down. So we need to use something called chi-squared distance. And this is a bit lossy, so we only get O tilde of epsilon close and TV distance for these things. I won't go into the details. Again, they're quite messy. And for mixtures, again, the ideas are similar, but much more involved. So if you want to see them, please see the paper. All right, let me conclude with some experiments. So these are experiments on synthetic data. What I did was I generated samples from a Gaussian with mean mu and variance identity. Then I corrupted a 0.1 fraction of them. Okay, and then I gave them to our algorithm and two popular alternatives, which are supposed to be robust, the geometric median and ransack. And you can see I plotted the L2 distance to the true mean as a function of dimension. And these two guys really do diverge as dimension grows, but ours stays really flat. In fact, the constant factor here is like really good. It's like really close to 0.1. So like our rate is like almost optimal, which is like really exciting. We also did some things for unknown covariance at a slightly smaller scale. So same kind of setup. I generated some points from a Gaussian with unknown covariance matrix, and then I corrupted some of the samples, and I fed them to ransack, which is the only alternative I knew of, and to our thing. And I also plotted the sampling error without corruption. So just like what would happen if I took the empirical covariance of the points without, without the corrupted points. And you can see that indeed the ransack algorithm diverges really horribly, but ours pretty much matches the empirical error, which is pretty good. Unfortunately, in this experiment, we only went to dimension 50. This is just because, well, in general, to learn the covariance to Frobenius error epsilon, you need like d squared over epsilon squared samples. And when d is large, you start to run into issues with like just everything fitting into memory. So to scale things up a bit, we took fewer samples, and then we went to dimension 100. And you can see, again, the ransack diverged, and we pretty much matched the error rate without noise. So we seem to be doing something quite nice here, at least on synthetic data. Okay. Is there a question? Or
yeah, a small question, Jerry. How do you exactly perturb the data?
Oh, yeah. So I tried a bunch of things, but it turned out that like for all of them, it was pretty much the same story. So I think for these graphs, it was a very dumb thing where I just like planted some small distribution somewhere. Like I like moved an epsilon fraction of points to be from like some other Gaussian.
Maybe that's specific. That's something that helps your algorithm more than other algorithms. That's what I'm trying to ask.
Yeah, so I don't think it is because I tried a bunch of different things and nothing really changed the picture. Perhaps there's some really certainly this is better constant factors than our analysis currently predicts. So perhaps in some truly adversarial sense we can do something worse, but I don't know. All right. So let me conclude. So we provide the first robust estimators for a wide variety of classes of distributions in high dimensions, which are both computationally efficient and provide these nice dimension-independent error guarantees. We do this by using higher moment information to move beyond naive outlier detection. And making this concrete, we give two algorithms for this intuition, which allows to trade off runtime and sample complexity, right? The filter and this convex program. Let me leave you with some kind of open questions and some subsequent work. The first and most interesting question, at least for me, is the question of is this really practical? Like, can we do something very non-trivial on real world data sets? And this is something I want to investigate further. Another interesting question is, can we do more distributions or more general settings? So there's been some work on this. There's a very interesting recent work of Charkar, Steinhardt, and Valiant, who investigate what happens when like the fraction of bad points is really, really large, like more than a half, say. And there you need to like redefine what it means to learn the distribution. But they give some very interesting results in that regime, which are kind of complementary to ours. And there's also some work by the California crew. So this is Ilias, Daniel, and Alistair, who like do some things for fixed structure tree-based nets. And then I also have some preliminary results on like what happens when you introduce sparsity to the mix. Finally, another interesting question is, can we get error which is O of epsilon, removing these log factors, which are like, they really shouldn't be there, and they like cause weird things that happen with like the breakdown points. And this represents this weird conceptual gap because pretty much in the literature, you never get these log factors. Like in robust statistics, either you get nothing or you get the optimal thing, right? And we have some results on this saying more or less, depending on the model, either in fact you can't remove these in a computationally efficient manner, or you can, but you have to be clever, and the algorithm is going to be more complicated. And finally, we have these two algorithms, which are like the filter and convex program. One is fast, but takes more samples, and one is slow, but is very careful with the samples. Can we like somehow combine them and get something which is fast and sample optimal at the same time? Okay, that's it. Are there any questions?
Thank you, Jerry. Any questions? One question is like, you can estimate the second moment robustly, which was the covariance matrix.
Right.
Can you estimate the fourth moment robustly?
So I mean, we end up doing something similar. It really begins to like now there's like information theory, the questions of like when is it even possible? Like how much can you screw up the fourth moment tensor just by perturbing the epsilon fraction of the data points? So you can get some, like it turns out what we end up doing is doing some sort of like spectral norm recovery of the fourth moment tensor, sort of. So you can get some results there. But again, for Gaussians, it's not too interesting. Although in general, this is an interesting question. If like,
and I guess like I mean the reason was that if you can go up till like it depends on the sense, but if you can go until 6 moments, then you can think about mixtures of Gaussians. So like mixtures of 2 Gaussians or something.
Yeah, so that's a very interesting question. Just like, can you do robust learning of like arbitrary mixtures of Gaussians? The problem is that like, so what we had here was this really nice proxy, which is more or less saying that the Frobenius norm of the covariance matrix minus identity or minus what it ought to be, like is a proxy for TB distance. Okay. It's not so clear that this is true when you go to like mixtures. Like you need to find the right function of the parameters, and this is trickier.
Jerry, I have a question about your algorithm.
Yeah.
Intuitively, would expect the worst case that the adversary puts all the points in one direction, pulls you towards that, but that's something that should only take you one step to detect.
Right.
But you said you can actually, it can happen that you need order these steps to.
Yes. So I actually tried to like get really O of D to happen. This is surprisingly difficult, but it definitely should happen in the worst case. It's like some sort of diffuse corruption where like it's the corrupted points are all in different directions, but the problem there seems to be that like if they're all in different directions, then they can't be pulling you too much in any one direction. So the spectral norm kind of is okay in every direction, which is kind of strange.
Right. So you're saying you do have an example? Or you think
there should be an example. I couldn't get it to like run in practice. I couldn't get it to actually execute like really D iterations in practice. I could get like some 10 iterations or something like this. But
okay, but this theoretically you have using. So what does the construction look like?
It should just be some sort of like diffuse distribution, which is just like say supported on all D directions, like but like say only in the positive ortho or something like that. So you generally push.
But then the average would be towards all one direction.
Right. So this is like the issue. So you can't actually do that. So you have to like be. Yeah, it's not entirely clear to me what the adversary would be doing there.
Again, why do you think it exists?
Just because. Like the analysis seems very tight for these tail bounds. It would be kind of surprising if you could get away with a constant number of iterations just from the analysis.
Okay, gotcha. Thanks.
So do we have any other questions? Okay, then I should take this offline, but thank you, Jerry. And this was the last talk of the semester, so we'll be back again in January, so stay tuned for this announcements, and thank you for joining us.